Hello, everyone. My name is Tesfahun Alamu. I'm a senior breeder at Ethiopian Institute of Agriculture Research. In this video, I will try to show you how to estimate regression and correlation using R. In this video, we will cover how we estimate correlation, simple correlation, multiple correlation, and the test of significance. And also we will see how to estimate regressions as simple regression, multiple regression, and test of regression. So after saying that, we will go directly to the R studio. So the first thing we'll do before any analysis is that to import the data. So to import the data, we can import from Excel, or we can import from the CSV file or text file. In my case, we'll import the data from the text file. So here, as you see, we'll have the data here. So example 1. So I'll import the data as example 1. Yeah, this is the data. So it have different locations, and the total observation is 135. Okay. So after saying that, I will start to how to calculate correlation, especially, and then from this correlation we'll start with a simple correlation analysis. So in order to see how is our data, so we'll see first the first part of our data, that is using the function called head. First part of our data. So as you see here, we have these are the five columns contained like location, year, treatment, protein, rep is the factor variables, but the measurement or the traits are also DMA, PLH, hectoliter, and yield. These four columns. The last four columns are the response variables. So we'll see how the correlation between these variables will be done. So in this case, for the first correlation, we can do the simple correlation. In the simple correlation, it means we will see the association between two traits, only two traits. So to see the association of two traits, first we can use a simple scatter plot can show us how the correlation between these traits happen. So in this case, for example, with this function, with this, it will attach for us the file name called example, and with the function plot will provide the x value, hectoliter weight, and the y value will be yield. So this color will be specified as black, or you can put here also maybe blue or green, anything. And then this type of the point will be defined using the PSH value. So 19 will give us the solid solid points. So with this, you can see how the association of our data will be between yield and hectoliter rate. As you see it, this is our data. So this shows that when you see this correlation, these figures from here and this one seems they are outlier from the total population. So it's necessary to remove these values from the data. So as you see from it, it is below 14. So we should identify the variables with less than 14 hectoliter weights, so that we can remove and then reanalyze, replot again. So in order to see, you should identify which is the row number or the observation number that contains this 0 and the value of hectoliter less than 14. So in order to do that, we can do in two ways. The first one is we can indicate first the example or the data file, and then we can indicate the columns from the data file what we have been interested to find. So and we specify the value that we are interested to identify. So here, for example, we have from the example data, based on the hectoliter, we should select the data those have less than 14 hectoliter weight. So when you run it, you will find those variables, those observation that have a hectoliter weight less than 14. As you see here, also this observation have the lowest value or the value less than 14 hectoliter weight. The other one is we can exactly identify varieties. The which function, this which function help us to identify from the hectoliter weight. We will identify which observation has for less than 40 value. So when we run it will give us for us the observation those have the value less than 14. Here in our case we have 4 observations that have the value less than 14, 46, 126, 128, and 134. So we should substitute this value with NA so that we'll eliminate from the plotting. So in this case, as you see here, we can do like that. So we first identify the 41 observation, and then we select the column and hectoliter weight, and then we'll substitute with NA. When we run this part, for example, from a data example with the row number 46 and the column name hectoliter weight, we will see the value. So here we have 34.2, that's similar to this one, so we will substitute it with NA. So we'll run it. And the same thing will happen with 126 observation and column number hectoliter weight. The same thing happens 0. So we'll substitute with NA. Similarly, all this will be substituted. Okay, like that we'll substitute, and so we'll plot again the graph to see how the relationship between yield and hectoliter weight. As you see it, the plotting will be now normalized, and we'll see how the distribution. So this shows that how there is a positive correlation between hectoliter weight and grain yield, as you see it, because there is it's have a positive trend, increasing trend between as hectoliter weight increase. Yield also increase. So this show how the strong positive correlation among these traits. Well, then the first one is we'll do is to estimate its correlation coefficient. The correlation coefficient for simple correlation can be estimated using the function called core. So this core function can be used to estimate the simple correlation between two variables. So with the attachment of the file example one, we use a function called correlation, and we'll provide the hectoliter weight, the first trait from the x side, hectoliter weight, and the y side yield. And here use indicate for us, for example, as you say use, if you see use, it will indicate the number of observations that can be included in the analysis of correlation. In this case, there is an abbreviation that uses everything, all. It will consider all observation, and there are a complete observation, means those observations have data with x and y. The other one is NES or complete, but this one also pairwise complete observation. This one especially interesting when you have more than one variables in the multiple correlation analysis, so that it will consider by taking two variables at a time, and it will, if all the variable is missing in one of it, it will omit, but and only consider those observation have we have value in x and y. So we will select this pairwise complete observation here in our case, and then the method is that show the type of correlation we can use. The Pearson one is the default one. There are also Kendall, and also there are Spearman correlation. So here we will use the default, so that Pearson correlation will be considered. So now we can run it. So here we have the correlation between this grain yield and hectoliter weight will be 0.4959. So in order to see this, if this correlation is significant or not, we can use a function from the base, our base function that called core test. This with attachment of this data example, this with will help us to attach the data for analysis, and then we'll indicate here only we can move consider NA remove true, because if there is NA in the data, it will remove from the analysis and it will test again for us. So if we run this one, it will give us the correlation value, and also it will provide for us the probability or the significant level of that correlation. So here, as we see, there is highly significant correlation between these two traits. So there is a significant relationship between yield and electrolyte rate, as shown in the graph. Well, after that, we'll see also the multiple correlation. To see the multiple correlation, first we should identify the possible variables that we consider in this analysis. To see that from our data, we can run the head function and see the first portion of our data. From our data, as you see, the quantitative rates are we will consider is DMA, PLH, electrolyte rate, and yield. The others are factor variables. So we should select this part, and so we can make analysis of correlation. So in this case, we have the function core, and we'll provide the column names of each variables to be considered. In our case, DMA, PLH, electrolyte rate, and yield. This is 6, 7, and 8, and 9. So this part will show the data frame with the quantitative trait or the trait so to be interested, the trait of our interest. So this is as you see it, we'll have only 4 columns that include DMA, PLH, electrolyte rate, and yield. So in order to analysis, we use the observation. We have complete observation with 2 pair of variables. So we made it the use as pairwise complete observation, and the method of correlation will be the default one that's called Pearson. So we'll run it, and if you see select and run it, we'll see the correlation coefficient among variables of these 4 variables. So this shows the multiple correlation among traits. And so now we will try to test the significance level of the correlation, the multiple correlation. So we'll have 2 functions that can be 2 packages that have a function that is helpful to test the multiple correlation. So this can be these packages are called agricoli and also biotools. So the first we use is from the agricoli pack from the biotool package. Each they call is multi-core test. So in this case, in the multi-core test, we'll provide the correlation coefficient of the multiple correlation coefficient. As you see here, R, we save it as R, the correlation, the multiple correlation. So we'll provide the matrix of correlation here, and also you can indicate the number of observations that been used to calculate this correlation. That's 135. Okay, then we'll run and we'll see the significance level. So here in the below the diagonal, it shows the p-value, and then above the diagonal, it will show you the star of the significance. As you said, 0.001 and above is with 3 asterisk, and 0.001 0.01 will be 2 asterisk, and 0.05 will have 1 asterisk. So here, more or less, we see highly significant correlation among traits also observed. The other function that can be found within agricoli is agricoli package. That is the correlation. As you see here, this correlation is correlation. As you see, the correlation is found in agricoli. So in the correlation, what we're gonna do is we will provide the data frame with the observation, the traits or the variables of interest to be calculated, the multiple correlation. And at this time, when it's calculated for us, it will calculate the correlation coefficient, and also it will provide us at the same time the p-value for the correlation test. So we can run it. So here, as you see, we have 3 matrices The first matrix shows us the correlation coefficient among traits, as you see here, and also the second table shows us, or matrix shows us, the p-value for the this correlation tests, and then the third one will show is the number of observations considered for this analysis. So with this we can get the p-value, so that based on the p-value we can estimate the test of correlation and which one is significant and non-significant. So in this case, as we see, there is a strong correlation coefficient almost in all all correlations among these traits show significance difference among them. Okay, the other part of this analysis is the regression coefficient. So in regression coefficient also we have two types, as simple regression and multiple regression will be considered in this tutorial. So for simple regression, we only consider one dependent and one independent variable. So in the regression coefficient, our interest is to show how the independent variables affect the dependent variable and define its relationship. So for the simple regression, we only consider a single variable of independent variable and a single variable of dependent variable will be considered. So as we see here, we can use the ln function, ln, and then from this ln we will provide the formula that is, for example, as a dependent variable we will consider yield, and the independent variable will be considered as hectoliter rate, and then we'll provide the data where this function can found these two variables. So when we run it, we will save this data with the name of this regression one. So in order to see the effects of this regression, we can run the summary. In the summary, we'll see one is the estimate, that is the estimate for each variable. For example, here the estimate of the intercept, and then the effect of hectoliter on grain yield. Especially when you see the simple regression, it gives us like this: b is the coefficient or the slope, and as a is, for example, the constant or the slope, then this one will be the regression coefficient of the. So when we write the regression coefficient or the regression equation from this solution, we'll have the intercept of minus 3707.8 plus 100.29 times of hectoliter rate. This is the regression equation. And also we can see the effect. Also using this effect, we can see how the intercept is, and so even we can get the coefficient using the coefficient function using reg1, and this one only provide the coefficient from the regression analysis. So the summary of ANOVA also, we can use the summary of ANOVA in order to see the regression analysis variance table for the regression. As you see here, we see since we use one trait only, we have 1 degree of freedom. So the total and the ANOVA analysis variance shows that there is a significant difference, or the significant contribution of this hectoliter rate over the dependent variable yield. This p-value shows that highly significant effect. So the hectoliter rate have highly significant effect on grain yield, and also it shows this hectoliter rate explained a better portion of the variability from grain yield. In addition, the equation from this regression coefficient shows that it explains that when hectoliter rate increase with 112.9 units, and the grain yield will improve with 1 unit. So this is how it will interpret. And then besides, we can also add, we can also use plotting in order to show the regression equation. or the regression line on the plot. So this can be done. First we can plot the scatter plot. Scatter plot will be plotted as we already shown in the above in the correlation part. We use to attach the example one, and then we plot hectoliter versus yield, and this is the color of the points will be blue, and then this 19 will PSH will give us the character of the point. So the character of the point 19 gives us the solid point. So we can run it. So here is how our graph. So from this scatter plot, we can add also the regression line. So this regression line can be added using the upline function. This upline function it will take there is a possibility to take the regression coefficient as you see here. So with this regression analysis is here, the output is regression one here we have saved. So we'll provide this the analysis output of the LM model so that we can plot it. This is color will provide red, and the line width is the width of the line of the regression what we have been plotted. So here, as you see, the regression plot will be look like this, so that we have positive relationship between hectoliter weight and grain yield. Okay, so this shows how the simple regression can be estimated using the R software. Okay, the next part will be multiple regression. This multiple regression analysis means we will use one dependent variable and several independent variable or explanatory variables. So in this case, we are interested to explain more variability of the yield using more than two and more than two variables or independent variables. So this we consider it as a multiple regression. So similar to the simple regression, we use the function called linear model, LN, and in this case, the only thing we differ is we'll add more than one variable. So these variables can be added as plus, plus, plus. So in this case, we will use, in our case, three variables will be as independent variables to explain the variability of grain yield. So here we'll run it. So when you see the summary of the ANOVA table here, we show that the total amount of variability explained by different rates is presented here. The maximum variability is explained by hectoliter weight, followed by dice to maturity, and followed by plant height. So as we see from the ANOVA table, we'll see that there is a highly significant effect of hectoliter weight on grain yield, followed by dice to maturity, and then plant height. Even if all of them have significant effect, but the hectoliter weight and the dice to maturity have more important to explain the total variability of grain yield. So in order to see the coefficient of estimate, we can run the summary. And here in the summary, as we see here, we see that the effects of each traits, and his intercept. There is also hectoliter weight. The effect is the dice to maturity and plant height, and we estimate the standard error for each of them. And then finally, we put the program puts the p-value and it's their significance. So here, as you say, the intercept is more importance, highly significant, followed by the hectoliter weight, and then the dice to maturity, and then finally the plant height. So this shows that how the significance of the regression coefficient will be tested in R. So at the same time, when you analyze it, it will provide you the ANOVA table and its coefficient, and also its associated test statistics will be presented. So in addition here, it will present for us also the R square or multiple, in this case we call it multiple coefficient of determination. So this multiple coefficient of determination shows that here in our case will be 0.366 and divided by and also its suggested value will be 0.2902. In this case, in order to estimate this multiple R square, here we need to sum up the total variability or from the ANOVA. We will take the total sum of square explained by the different trait, like here, for example. This is the square of due to hectoretroid. This one from due to days to maturity, and this one will be due to plant height. And then this one will divide by and then we'll add one more, that is the residual. Okay, so generally R square is sum of square for regression divided by sum of square for sum of square of total. So it shows us this part shows that the total sum of square over the sum square of total means this part shows that the total sum of square explained by regression, the portion of the total sum of square of explained by the regression, as called this multiple coefficient of determination. So when run it, you'll see it, the value. So this value, as you see it, is 0.0658, as you see here in this analysis, 0.066, almost identical. So that's identical. So this is how they calculate the total sum of coefficient of total multiple. This shows that how to estimate the multiple regression coefficient for the regression model. So our regression model for predicting is this one, yield. The intercept is 5725.50, and also we have plus 80.29 hectoliter plus 18.9 days to maturity and 16.6 plant height. So this is how we estimate the regression coefficient, the multiple regression using R. So this explanation is here, for example, is when we make it constant with other variables constant, with increase of 8.29 hectoliter weight unit, it will increase 1 unit of grain yield. So in such manner, we can use R to estimate the multiple regression and multiple regression and simple regression analysis. So in this video, we see already how to estimate simple correlation, multiple correlation, simple regression, and multiple correlation, and its associated tests. So this all we have on this video, and we'll see you again. I will see you again in the next one. Thank you very much.